All right, so this is Gavri Philipson presenting writing modules in Rust.
So I'm Gavri from Redis Labs. I'll be talking about developing Redis modules in Rust. So who of you has ever used Rust before? OK. And who here has ever written a Redis module? Oh, cool. So I guess the people who have been writing modules have been using C, which was the language of choice until recently. So I'm going to try to convince you why writing Redis modules in Rust is a good idea. So first of all, what is Rust, since most people are not familiar with it yet? Rust is a programming language from the Mozilla company or organization. They actually started developing Rust as a solution to all the security holes in web browsers. When you write code in C or C++, it's very easy to make mistakes that introduce security issues, and Rust tries to avoid all that. So its main points of the best thing, about Rust are that it's blazingly fast. It's as fast as C or C++. It's memory efficient, which means it's really easy to plan your memory layout as you do in C and C++. You know exactly how much memory is used. And it's safe, which is the big selling point. So you can write code that's efficient, but it's also safe. And we'll talk about that a bit. Rust also has a friendly compiler. Some of you may have used programming languages when you make an error. The compiler gives you a whole screen of text, and you have to try to decode what that means. Rust really tries to be friendly. And it tries to explain to you what you've done wrong and how you can do it differently. And it gives suggestions that are very helpful. So it's a great way to learn the language, just to try things and see what the compiler says. And it has cargo. Cargo is fantastic, a fantastic idea. It's both a package manager and a build system. So these are two big problems. When you write code in C or C++, it's always an issue. How do I build my code? Do I use make or CMake or something else or a proprietary system? And more modern languages, they have their own build system together with the language. So Go, for example, does this very well. If you write Go code, it's very simple to build it. You don't need to write make files or stuff like that. So Rust does the same thing with Cargo. But Cargo also solves the dependency management problem and the packaging problem. Go struggled with that for a long time. And as you all know, things like NPM and Maven, it's always a big issue. How do you manage dependencies? So Rust comes with all that out of the box. And Cargo does it for you, and it pins dependencies, uses semantic versioning. So it's really, really, really easy. You don't need to learn a whole host of other third-party tools. So what are Redis modules? Just to recap, you've been hearing a lot about them in the keynote. So Redis modules are a way to add custom functionality to Redis. Two of the main things that modules can do is add new commands and add new data types. So for example, Redis time series or Redis graph or Redis search all do these things. They add new data types and they add new commands that you can use. So if I want to create a module, that are usually the things I want to do. So why would I want to use Rust specifically for writing Redis modules? Well, it's amazing how much of a good fit the philosophy of Rust is with the philosophy of Redis. Redis is all about speed, low latency, efficiency, small size, and Rust fits that model very well. So Redis modules run in the same memory space as Redis. They become part of the Redis process. So if you do anything bad in your Redis module code, for example, you do a bad memory access, null pointed reference, whatever, you can crash the whole Redis process. And memory leaks will waste precious Redis memory. Redis memory is the main asset that we manage, and we want to do it efficiently. We don't want to bloat it with unneeded stuff. So we want something that's efficient, but it also enables us to manage memory safely. And that's exactly what Rust excels at. As I said, speed. Redis is single-threaded mostly. So if we want something inside a command, it holds up the entirety of Redis for that time. So we want to do that as fast as possible. So Rust introduces safety, but it doesn't come at the expense of performance. Performance is exactly the same as native C and C++. So, unlike the saying goes, we can have nice things. So, why not write in C? How many of you like C? How many of you? Okay, great. How many of you don't like C? Okay. I actually do like C. I think C is a great language. C is fantastic. C is from the 70s. It came out in 1972. I'm from 1974, and my kids think I'm ancient, so C is pretty much an old language. It doesn't mean it's a bad language, but at the time it was revolutionary. It's great for writing operating system kernels, which is what it was used for initially to write Unix, which was originally an assembly language, to rewrite it portably in C. It's very close to the hardware, it's very close to the machine, which is great. If you want raw pointers, raw memory access, pointer arithmetic, C is a great language. It's also a small language, it's relatively easy to understand. But if you have a larger project, and it grows and grows and grows in lines of code, it becomes very, very, very hard to maintain. So it's very hard to justify writing user-level code in C in 2019. Kernel is something different. Memory management in C is handled explicitly by the developer. So we all know malloc, free. We all had bugs like double free or memory leaks. And so the Mozilla guys say that most of the security problems in Mozilla were actually caused by double freeze and by buffer overflows, which are both things that are very easy to do in C. And Rust tries to avoid these things, and it does so by giving you very strong tools to avoid these two problems. And the third thing in C that's hard is error handling. So if we want to open a file in C, we call open and we get back something that's a file descriptor. But it might not be a file descriptor, it might be a negative number, and then we have to go find out that it's an error code, and we have to look up the error code and see what happens. It's very easy to forget or to mishandle. So it's not ideal. So I know, let's use C++. It looks great, right? It does everything that C doesn't do very well. It does it better. It has exceptions for handling errors. And, well, it's an enormously complex language. Any of you program in C++? Nobody? OK. So C++ grows and grows and grows and grows and grows from year to year. People say, oh, you should look at C++. The newest versions is great. That's true. It's much less worse than the older versions. But again, it's a huge language. It's complex. And it doesn't let you write safe code, because it does introduce things like like smart pointers to manage memory. But it still includes all of unsafe C inside. So anything you can do in C, you can do in C++. Any error or bug you can introduce in C, you can also introduce in C++. And, well, error messages. Yeah, if you write code, especially with templates, good luck debugging. So there are lots of other languages that came out in the meantime. I put up some of the more prominent ones here. So, of course, Java and JavaScript in the mid-90s. Great languages, but very unsuitable for writing Redis modules. Java is a huge virtual machine, and it uses garbage collection. Garbage collection is fine for certain kinds of applications, but not for sub-millisecond latency inside a request. If you do garbage collection, and certainly you have to stop the world, or even if you don't stop the world, they have a smart garbage collector, you don't want to wait 50 milliseconds or even 5 milliseconds for that. So JavaScript, same idea. You can embed it, but it's large, it's fat. So what's interesting is that Scala introduced functional programming to the real world. Functional programming is something that you either like or don't, and there are zealots who say that everything should be done in functional programming languages like Haskell or Erlang. But in the real world, people don't use these languages too much. They are pretty much niche. But Scala really became a mainstream language, and it introduced functional programming concepts, which is important to us because Rust has many of the same concepts and even similar syntax. And the very interesting fact is that modern languages like Kotlin, Java, TypeScript, and Swift all have very similar feature sets and also have very similar syntax. So if you look at these languages, you look at code written in them, it's very similar. And Rust also uses that same syntax in many places. So if you look at how to manipulate collections or do transformations, it's very similar also in Rust. So it's easy. I did mention Go here, but Go suffers from the same problems as Java does. It has garbage collection, it has a runtime. Rust doesn't have a runtime. So if you want to put something inside something else, the smaller it is, the better. Okay, show me the code, yeah? So let's see, look at this program. Does it look familiar? Yeah, that's because it's C, okay? This is not Rust, it's C. The reason I'm showing it here is I'll compare it to the Rust version and we'll see what's the same and what's different. So for those not familiar with C, we're defining a simple structure called person. Inside it has a string, which is the name, and it has an integer, the age. And then in the main program, we create an instance of that person named Joe, age 25. And what we do is we take a reference to that person, and we store it inside a pointer named somebody. So somebody is just a pointer to that structure that you created earlier. It's not a copy. It points to the location in memory where that structure sits. And then we want to print the contents of our structure. We do that by dereferencing the pointer. So the arrows after somebody, arrow name, somebody, arrow age, it means take the pointer, follow it, dereference it, and then take the value that it points to. Then take the value inside the structure that it points to. Which in C, of course, can fail. If somebody is a null pointer or it has been freed already or something like that, we get a crash. So let's look at the same program in Rust. So it's pretty similar. Struct person. One of the things that comes to the eye immediately is the order is the other way around of the type and the name. C actually was a language that changed the convention. The earlier convention in Pascal, for example, was you put the name of the variable and after that the type. The name is the important part. The type is just less important than the name. And in C, they thought it was a good idea to remove keywords for defining variables and functions, which makes it easy to compile, but sometimes hard to understand. If you look at function pointers in C, for example, it's very hard to understand what goes on. So Rust came back to the more intuitive syntax, like all the other languages I mentioned before, TypeScript and Kotlin, etc. So this person has a reference to a string. The static word means that it's a static string that's compiled into the code and compiled into the binary. It's not a user-supplied string. That's very important in Rust because in C you can just pass a pointer. What happens if name is freed, for example? If we have a structure and we have a pointer to the structure and the value inside the structure goes away, there's no way to know that in C. But in Rust, you have to tell the compiler the lifetime of the references inside the structure. So we tell the compiler, don't worry, this string is not going away. It's a static string. We wrote it, hard-coded into our program. So as long as the program lives, this string reference is valid. So that's just the tip of the iceberg regarding lifetimes. It's a pretty complex feature, but it helps you write code that can be very, very efficient. You can pass references around, but they won't disappear from underneath you. It's impossible. It's statically checked by the compiler at compile time. And i32 is a 32-bit integer. In C, again, int, you don't know what its size is. It can be 32-bit or 64-bit. In Rust, every type has a predefined size. And then we look at the main program. First of all, Rust has type inference. So we don't have to tell everything what the type is. We can just say let person be an instance of a person. And we can say let somebody be a reference to that person. We don't have to say somebody, the type of it is a reference to a person. We can do that if we want, but we don't need to. The compiler does type inference, which makes it very readable and easy to write code. Everybody was written, for example, iterators in C++ or Java, and you say just person, 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 person so many times in the same line. You don't have to do that in Rust. And finally, the last line, you don't have to use an error operator to dereference. The compiler automatically understands that you have a pointer, or actually a reference, and it will automatically dereference it for you. So unlike in C, we don't need to differentiate between if the structure is directly available or if you need to follow a pointer. We just use dot notation, and the compiler inserts the dereference automatically for us, which is very convenient. Another thing about Rust is that the default is immutable. So we can't just go and change a field of a structure or anything else. Once we create a variable, the variable is immutable. This makes it very easy to write safe code. Things won't just change underneath you if you pass something to a function, or if you look at the beginning of a function and the middle of a function. You know that the variable has been created. It won't change. But sometimes we do need to change things. So we have a specific keyword called mute. So we say let mute person, well, sorry, mute person is not a good example, but let this mutable variable refer to a person, and after that we can change the values inside the person. So we have to specify. It's the opposite from, for example, C++, where everything is mutable and you have to say const on things. Mostly in the functional programming world, people want things to be immutable, and it's very easy to reason about this code. Okay, generic containers. So generics is a big issue. Go, for example, has been struggling with this for years. It doesn't have so-called generics in the language. They're working on that. Everybody who used Java or C++ will be familiar with the syntax. So we have a structure called the vector. It's part of the standard Rust library. A vector is like an array, but it's growable and shrinkable at runtime. So if we look at the definition of this vector in the Rust code, inside it has a buffer which has the actual data, and it has a length which knows how many items are inside. The T notation means anything. We can put anything inside. And at compile time, like in C++, the compiler will put in the correct type. So we create a mutable variable named languages. It's a vector of string references. And we initialize it as a new vector. Rust doesn't have a new keyword. It just has the convention that constructors are named new. And then we insert 3 values into this vector. And now we have a vector with the 3 string references inside it. This is a bit boilerplate. If we look at this code, it's very common to create a vector and put values inside. It's also not very efficient because we have to pre-allocate the vector, and then we put values inside it. It may have to grow. If we know that we're going to put 3 values inside, we can pre-allocate it with a size 3, and there's no reason to let it grow at runtime. And also, the variable here is mutable, which is not very good because we want just to initialize it, and then we want the variable to be immutable afterwards. So it would be great to package all this up into something like a function that can do it for us. But if we would try to put this in a function, it would introduce some inefficiencies. We would need to pass the values to the function somehow and tell it what to do. So Rust has a very strong feature called macros. Macros lets you avoid boilerplate by adding new syntax to the language. You as a developer can write your own macros and add syntax to the language, which is used at compile time. Macros are work together with the compiler. The compiler, as it compiles your code and builds the abstract syntax tree, it processes the macros for you. So unlike C, for example, where the preprocessor is just text processing and you can do all kinds of weird stuff, it's a hygienic macros, like in Scheme or other functional languages. Macros cannot, for example, shadow built-in identifiers by creating new identifiers. They can do very specific things, but they're very strong. They can manipulate the syntax tree and do anything. So Rust includes a standard macro in the library called vec. Macros end with an exclamation mark, or bang as it's called. And this introduces new syntax. It's not calling a function named vec and passing it 3 arguments. It's just at compile time, it's causing this code to be written, and it also pre-allocates and does everything else for you. So this is a very efficient way to create a vector, and it demonstrates the strength of macros. One other great thing in Rust is sum types. So, of course, Rust didn't invent sum types. Rust tries not to be original. It tries just to take good ideas from other languages and put them together. So sum types are very popular in functional languages. We're all familiar with product types. So the struct that we saw in one of the first slides is a product type. It means it has various values inside, and you put together all of them, and you pass them in one unit, a struct, or an object, or a class. Sometimes are different. They include one value from among a limited set of possible values. So, for example, if I want to represent either this value or a third value, I use a sum type for that. And it's a very efficient way to represent alternative values. It's a bit similar to a union in C, but unions are the extreme end of unsafe. You can put something inside a union and access the wrong field of the union, and you will get garbage. So sometimes are a safe way to do that. So the syntax for some types is using the enum keyword. It's very different from the enum in C. Enum in C is much simpler, just lets you define a set of integers. So the enum in Rust lets us define a number of alternatives. This would be similar, for example, to creating a base class in Java and derivative classes from that base class. And then you can put the base class inside some container, and it can be either the base or some of the derivatives. But then you cannot limit, for example, other people implementing more values. It's a bit creaky. So the sum type enum does all that for us. So if we want to represent a JSON document in Rust, we can create a sum type named value, which can represent anything that can go inside the JSON document. So JSON value can either be null, or it can be a Boolean value, or a number, or a string, or it can be an array, which means it includes some other JSON values, or it can be an object, which maps a string to a value. So anybody who's ever used JSON is familiar with this. So the sum type lets us specify alternatives, but each alternative can also include its own associated data with it. So this is a very succinct way to represent a JSON document in Rust. And actually, the standard Rust library for processing JSON uses this exact definition. I just took it from there. So if we put together sum types and macros, what we get is the following. We can define our own custom syntax in Rust for creating JSON documents. So in Python or JavaScript, for example, you would use a dictionary to represent a JSON document, but that's not type safe. Nobody's going to check that we put the correct value in the correct field. So here in Rust, we can create new syntax. The JSON macro is also part of the standard JSON package. And here we have syntax that's not valid Rust. In Rust, there is no dictionary syntax in mapping a string to a value, but the JSON macro adds that. And here we have a very intuitive syntax for creating a JSON document, which will actually create a data structure of the kind that we saw before. So it's type safe. We can traverse it with code, and we can know exactly what the values of the types are, what the types of the values inside are going to be. Now, how do we get the values back out of the sum type? For that, we use pattern matching. Okay, pattern matching is the twin brother of sum types. Once we created a composite sum type with stuff inside, we use pattern matching to get it back out. So in some languages, you would have to, for example, use reflection to walk over a data structure and take things out, which is very slow and very unreadable. Pattern matching lets we specify by example what I want to do. So I have this value which can include either of these options. So I write a match statement that says, take this John variable and look what's inside. So, and I want to return a string representation of what's inside. So if there is a null inside, just return the string null. If there is a Boolean inside, then take the value inside the Boolean, put it in a variable named b, and then we can use that variable. So whatever value is inside is extracted and put in a variable of the correct type. It's very easy to handle values that way. OK, so that was Rust. Let's write some Redis modules in Rust. So there is some prior art by other people that I looked at, found on the internet. which does development of modules for Redis in Rust. None of them provides a complete toolkit to do so. And we at Redis Labs are working on providing a complete toolkit to write your own Redis modules without having to reinvent all that stuff. Unfortunately, for me, it's a side project, so it's not something that we can say when it's going to come out. But it's very interesting. So let's look at Redis modules. So if you want to write a new Redis command in C, you need to create a function that looks a bit like the following. This is the prototype from the Redis modules header file. So I have to write a C function that returns an integer, which is an error code if something goes bad, or OK if everything goes OK. Inside, Redis will pass a pointer to context, which we can use to get arguments and things like that. And then it passes a list of strings for the arguments that were passed to the command, and the length of the list. Okay, so this is very similar to how you write a main function in C. You have the argc and argv, the arguments from your operating system. In C, because there's no way to know the length of the lists of values, you have to pass it explicitly. You have to say, we have this and that number of arguments, which is very easy to get wrong. If you do a loop and you get it wrong by one off, then you crash again. So what we can do, the first step would be to write a function with the same signature in Rust. So Rust has a very good C FFI. FFI stands for Foreign Function Interface. It's the way that we can interoperate with C. And Rust has a very good and efficient FFI for C in both directions, either Rust calling C code or C calling Rust code. In our case, we need both for writing a Redis module. So this function is something that C can call for us. So the extern keyword means that its function uses C calling conventions. Normally, Rust has its own calling conventions, but this exports a function that's compatible with C calling conventions. So this is the same signature. It's just written a bit differently because it's Rust. So first we put the name and then the type. And we can't use regular pointers in Rust. We have to say if they're mutable pointers or constant pointers. So a star mute means a regular mutable C pointer. In Rust, this is called a raw pointer. You don't normally use them in your Rust code because they're unsafe. They can be null, for example. So if you dereference them, you crash, or they can be freed or whatever. So in Rust, you normally use references like we saw before. But you can, if you need to interoperate with C, you can use raw pointers. So this is compatible with the previous function. So if we'll look again at the C code, we want it actually to do something. So we look at the number of arguments, we check if it's correct. And if there's a problem, we call this built-in Redis function called Redis module wrong arity, which is a geeky way to say you pass in the wrong number of arguments. Otherwise, return Redis module OK. So doing this in Rust would be very similar. If argc is not 2, then return and call the built-in function. It's very simple. You don't have to say anything special. We just call the built-in function. Unfortunately, or rather fortunately, this code will not compile. The yellow part will not compile because it's unsafe. We take this pointer context, a raw pointer. We pass it to another function. We have no idea what the other function is going to do with our pointer. It might dereference it, for example. So that's unsafe. So if we want it to compile, we have to put this inside an unsafe block, which tells the compiler, I guarantee to you that the code inside this block is safe. We're calling an existing Redis function, which we assume to be correct. So that's not a problem in this case. OK, so this is how we integrate safe code with unsafe code together. Well, OK. This doesn't look like Rust. It looks like C with a weird syntax. So why in the world would I want to write C in a more complicated way just to do it in Rust? It doesn't make sense. So what we would like to do is use idiomatic Rust to do that, which will look quite different. So to explain how we would write this function, which is very C-like, in idiomatic Rust, I'll talk a bit about error handling. in Rust. So as I said before, in C, if you open a file, this is Rust syntax for opening a file. So in C, if you would call the open system call, you would get back a file descriptor, which could be a negative number, and then you have to look up the global variable or no to see what's happening, and you can easily forget that. In C++ or Java, if you open a file and there's a problem, you get an exception, which means you have to remember to handle that exception or you will be surprised at runtime. Java tried to do type-checked exceptions, but it didn't really work out, so exceptions are a problem. So in Rust, it uses neither return codes nor exceptions. It uses sum types, of course, to handle errors. So in Rust, there's a built-in sum type called result. It's one of the most common sum types used in Rust. Result can include either a value or an error. But an error is just a standard value as well, okay? The language doesn't tell us what the error has to be. We can put anything inside. We can put a string inside, or we can put a structure with more detailed information inside. The point is that most functions that can fail return results, which means that we, as the caller, have the responsibility to check the result and see what's inside, whether it's okay or whether it's an error. We can't forget to do that because we won't be able to access the value without actually inspecting the results. So result is an enum, a sum type, which has two options, either okay or error. There's no magic behind it. It's just two plain values. The magic is that all the functions in Rust use the same convention. So we can easily build chains of functions, calling other functions that all return results, and we can handle them in a central place. Go, for example, uses the convention of returning multiple values from a function. It returns a value plus an error, but you can easily forget to check that error. So here, you can't forget it. So we use pattern matching, as we saw before, to inspect the result and to get back out the value. So inside the match statements at the bottom, if the value was okay, if the result was okay, we retrieve the file that was inside it, and we can access it directly. And if it was an error, we retrieve the error, and we can print it or do anything else. So this is a very convenient way to handle errors. You can't forget to handle them, and you use the standard Rust idioms. So looking back at this previous code, we would like to write functions that look like this in Rust. So first of all, the context would not be a raw pointer. It would be a safe Rust reference, which cannot be null. The arguments, there's no point in passing a list of pointers and a length. In Rust, we have a vector, so we can just pass a vector of strings. And the result shouldn't be an integer. Nobody remembers if this integer means an error code or if it means the size or whatever. In Rust, it's very simple. We return a result of something that we call a Redis value or a Redis error. If there's a Redis error, the framework for us that we are writing at Redis Labs will return an error message. If it's a Redis value, it will serialize it using the standard Redis module commands and send it to the user. So this is very easy for the end user who implements the module to use. So this is how we'd use it. We just check the length of the argument, and then we don't have to call any Redis module functions directly. We just either return an error or return a Redis value inside. This looks much more like idiomatic Rust. Unfortunately, however, if we want to use such syntax, we need to write a lot of boilerplate code because every command that we implement has to be callable by a Redis. So Redis won't be able to call this function. It won't know how to do it with the Rust calling conventions. We need some translation layer that automatically creates a C function for us that can be called by Redis, and the C function will call our code. So of course, the solution to that is to use macros. So we wrote a macro called Redis command. What it does is take the Redis context and the name of the command and the standard Rust function, and a couple of flags that Redis can pass, such as if it's read-only or read-write. And this macro will generate the code at compile time that does the conversion between the C calling convention and the Redis calling convention, does the serialization, the error handling, everything for you. So you just can pass a very simple Rust function. And we defined a second macro called Redis module, which does all the initialization. So there's also a lot of boilerplate. When you initialize the Redis module, you have to set up a bunch of function pointers to the commands, and you have to give it all kinds of information. So we hid all that behind another macro, so you don't need to be exposed to that stuff. So what we see here is a complete Redis module written in Rust. It can hardly get simpler than that. We have a function called hello. As we saw before, it gets the context and it gets the arguments as idiomatic Rust data types, and it returns a result. Inside, we do some stuff to retrieve the argument that we're interested in. I'm not going to talk about the syntax. It's very similar to other functional programming languages. It's just a chain of processing where we get something from an iterator and we skip the first value and then we get the argument. The first value is the name of the command, which doesn't interest us. No, does not interest in. Sorry, which we're not interested in. And then we use the key. We create a new string greeting, and then we just return the greeting. The into command is a standard Rust idiom, which lets us convert values from one type to another type. So we have a plain string, but we need to return a Redis value, as we saw before. So we can set up a converter, which is automatically called by the compiler, which will convert our string to the Redis value. It's fairly standard to do that in Rust. So at the bottom, we call the Redis module macro. This is new syntax. There's no such syntax in Rust. This looks a bit like a struct, but it's different. And we pass it the name of the command, and we pass it a list of commands that we want to create inside. The name of the module and the list of commands that we want to create inside it. And this does all of the magic for us. So to run the module, we start the Redis CLI. We say module load, and we load it from a shared object. Of course, Rust compiles our code to a standard shared object, which can be called from C or anywhere else. We give the command, and we see that it works as intended. If we didn't pass the commands, it gives an error message. If we did, it gives us our formatted string. So you can check out the code. It's open source. It's on GitHub. It's still in early stages. And if anybody is interested in it, contributions are welcome. Questions, anything, feel free to contact me if you're interested. Thank you. So we have a couple of minutes left for questions. Are there any questions?
Hi, how are we going to handle the memory allocation APIs? Because Redis module alloc and Redis module free.
Yeah.
And Redis module also does automatic memory allocation.
That's a very good question. So the question was, how do we handle memory allocation? Redis does its own memory allocation, so it can manage, for example, LRU caches and expiry and things like that. So you don't just call malloc and free. Normally Rust will allocate its own memory, and Redis wouldn't be aware of that memory. So if you do info, it wouldn't show up. So what we did is we wrote a custom allocator in Rust, which hooks up to the Redis allocation commands. It calls Redis alloc and Redis free whenever you allocate, for example, a vector or anything else in Rust. So it works seamlessly with the Redis memory allocator.
It's part of the...
Yeah, it is part of the SDK.
Did you get to benchmark the...
Yes. Again, it's preliminary. One of the things we did is we started re-implementing the Redis JSON module in Rust. We want to add more features to it, and we prefer not to maintain the old C code, so we started rewriting it in Rust, which was pretty simple to begin with. And we also want to integrate it with Redis Search, which is something that we hope to do more following up the announcements of the multi-module Redis model. The performance is mostly the same. The benchmark we did, mostly the same speed, maximum throughput. There's no penalty.
Because you had one additional function called the wrapper before going to the Rust call, right? So
That's right, but,
But it
it
is
didn't
not
turn out to
expensive. Okay,
be
cool.
expensive.
Okay,
Yeah.
and final question: does Rust have any features like Go routines that you have in Go, so that you can have cheap
That's a very good question.
concurrent?
That's a very good question. So, does Rust have anything like Go routines or green threads? So, actually, a few years ago, it did have them in the standard library, but they removed it because it requires the use of a runtime and it requires a solution for split stacks and or segmented stacks, which complicates it a lot. So, they took it out, and Rust has no runtime. But there is a third-party implementation for something like Go routines. And they are working on support for async and await keywords inside the language, so it will be very easy to use. It's something that's, I think, in the next years coming to Rust. Any other questions?
Any other questions?
Or Yuri? Yeah.
So is the idea that going forward, you would encourage people to write modules using Rust, or is the C API going to still be there and it's equal support for both?
Well, the actual API of Redis is still the C API. This is a layer on top of it. So I would definitely encourage people to write modules in Rust because it's much more fun and it's much more safe. But it's not going to come at the expense of the ability to write modules in C, of course. Okay.
Do you have any examples of small applications or uses for modules that like developers might build themselves, something that Redis wouldn't necessarily take on? So big.
Mm-hmm. Yeah, so the repository here includes some examples of very simple modules, and we also have the new implementation of Redis JSON online and on the same location. It's far from being finished, but it can serve as inspiration.
And do you have any testing frameworks for making sure, like testing your modules against Redis itself?
Not yet. It's planned.
Any other questions?
Okay, thanks everybody.